Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations, Section 2, Solving Trig Equations, Video 4, Basic Quadratic Trig Equations, Part 2. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned to solve a basic quadratic trig equation. We used a substitution to transform the equation into a purely algebraic equation with no trig functions, solved that equation, then reinserted the trig functions by undoing the substitution. At that point, we were solving basic linear trig equations. In this video, we will look at two more examples of basic quadratic trig equations. Now, sometimes the solutions to the quadratic equation will not lend itself to nice trig solutions. For example, let's solve cosine squared theta minus cosine theta minus 1 is equal to 0. This is a basic quadratic trig equation. It only has one trig function, but the highest power is 2. Now, there's a lot missing here. Okay, maybe there's not a whole lot missing. I just bypassed a lot of the algebra. But as far as the substitution moves, we would let cosine theta equal u, which will transform the equation to u squared minus u minus 1 is equal to 0. Now, that won't factor. You can try if you would like to, but you can use the quadratic formula. And since this isn't a video about how to use the quadratic formula, I'm just going to assume that you can apply it and get u equals 1 plus or minus the square root of 5 over 2. I will remind you that the quadratic formula says if ax squared plus bx plus c equals 0 and a is not equal to 0, then x equals negative b plus or minus the square root of b squared minus 4ac over 2a. If you're not confident that you can get there, pause the video right now, apply the quadratic formula to u squared minus u minus 1 equals 0 until you convince yourself that you can get u equals 1 plus or minus square root of 5 over 2. These are clearly not nice values for cosine. By the way, we undo the substitution now. We change u back to cosine of theta to get to cosine of theta equals 1 plus square root of 5 over 2, and cosine theta equals 1 minus square root of 5 over 2 by separating these two values and changing the u back to cosine. Now, we have a protocol for solving basic trig equations, linear trig equations, when the value over here is not nice. We just use inverse trig functions. But be a lot more scrutinous, a lot more observant when the value is messy like this, because you may not know what it equals as a decimal. Now, for cosine theta equals 1 plus square root of 5 over 2, you might be tempted to look in quadrants 1 and 4 for solutions, since 1 plus square root of 5 over 2 is positive, and cosine is positive in quadrants 1 and 4. However, as a decimal, 1 plus square root of 5 over 2 is approximately 1.6180. That's greater than 1, and hence cannot be the value of cosine. The range of cosine, remember the graph, is between negative 1 and 1. You cannot take a cosine and get a value bigger than 1. If you tried inverse cosine, it would tell you domain error, and that's your signal that this part generates no solution. Well, it's not a real solution. There's a complex solution, but that's beyond the scope of this course right now. So no solution there. And when we look at the second one, let's observe that 1 minus the square root of 5 over 2, although it looks positive, because of the minus, has the propensity of being negative, and it is negative. It's about negative 0.6180. Now, this is in the range of cosine. It's between negative 1 and 1, and so solutions exist in quadrants 2 and 3 because that's where cosine is negative. So let's look in quadrants 2 and 3 and do what we do. First, we got to find the reference angle. So we'll do cosine inverse of the negative of this fraction, which is approximately 0.9046. Now, why did I put the negative here? Because our protocol is to find the reference angle, which is acute, which means we take the inverse trig function of the absolute value of this constant. But this constant was negative. And so sticking a negative in front of it turns it into positive. Now, had you not put the negative here, let's see, cosine being an even function, had you not put the negative there and done inverse cosine of what you see, then where it would have to give us a value where cosine is negative, and that would be over in quadrant 2. So this would have given us a non-acute angle. So again, a little bit sneaky there, but that's what happens sometimes when you got these expressions where it's not clear if they're positive or negative. So cosine inverse of the absolute value of the expression, which is the negative of this, is 0.9046. And now that we have that and we know it's in quadrants 2 and 3, then we just measure it from standard position like we normally do. In quadrant 2, it's pi minus 0.9056, which is approximately 2.2370. And in quadrant 3, that should say quadrant 3, so we'll just add a 3 there. In quadrant 3, it would be pi plus the reference angle, which is about 4.0462. And so our first period solutions are these two values, and then the general solutions are just those two values plus 2 pi n, where n is an element of the integers. Now, I do have another example, but this video has already gone a little bit longer than I wanted to, so we're just going to stop right now and do a follow-up video.